Hello, everyone. Okay, now let's continue on with this lecture, and I think we should be able to finish in this video. Okay, so let's draw the Lewis structure for boron trifluoride. So if we translate the name, we have boron. And then 3 fluorine atoms. Okay. So sometimes you get electrons where they don't form an octet. Boron is one example. So boron here is in group 3. So boron has 3 valence electrons. Then fluorine, like chlorine, has 7 valence electrons. So 7 times 3. So if we sum those electrons together, we get 24 electrons in total. Okay, there we go. So boron is going to be our central atom. And this is a special case because fluorine will surround boron in approximately 120-degree angles. And then we have 6 electrons in bonds, so that means 18 electrons remain. And what happens then is we put the electrons around the fluorine atoms. So now fluorine has an octet, but boron doesn't. Okay. So boron is the exception where boron prefers a sextet or 6 electrons. So first only have 6 electrons surrounding it. Okay? So we can say that atoms that form strong double or triple bonds are these elements only. C, nitrogen, oxygen, phosphorus, and then sulfur. So we'll encounter some cases where chlorine may be able to form a double bond, but that's usually when chlorine is the central atom and not the terminal atom. Okay, so let's now let's kind of revisit this boron structure. Could the following structure be written for BF3? Okay, so this structure, although it looks kind of weird, well, it's not out of the ordinary, right? So yes. So this structure is perfectly valid, right? Because fluorine has, everything has an octet. Now boron has an octet, but if we do this, now we have a negative charge on boron and a positive charge on fluorine. Okay? So while this is okay, it's typically not what we draw. So let's just explain why. Yes, it can, yes, it can, because now all atoms have an octet. So that's a perfectly fine structure. Okay. But however, there's something we need to point out. However, based on data about what atoms form double bonds, neither fluorine or boron are known to form multiple bonds. With other elements. And this is particularly the case for fluorine because fluorine is so electronegative, it wouldn't want to share more than at least 2 electrons with another element. So this structure is probably not a good one. And another reason is because you form a positive charge on fluorine, and we'll soon learn that when we draw formal charges, we want the negative charge on the more electronegative atoms. So this structure wouldn't make sense because it's creating a dipole, a charge structure, and that doesn't make sense given the charges that we have drawn here. Okay, let's move on. All right, so there we have not enough electrons. Here is where we have, okay, sorry, I should have fixed this. This should say too many electrons. Okay, so sometimes we get structures where there are too many electrons. So that's definitely something we do see here as well. All right, so let's draw the structure for sulfur tetrafluoride. So sulfur tetrafluoride for fluorine atoms. So remember, sulfur is 6 valence electrons. So here we only care about the valence electrons. And then fluorine is going to be 7 times 4 again. So this will give us 28 electrons. And what we end up with is 34 total electrons. Okay, so what we did before, we're going to draw sulfur in the center. Then let's draw 4 fluorine atoms around it. Okay, so we already have 8 electrons. Now we need to put 26 more. So if we add electrons around fluorine here, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But now we need to put one last lone pair somewhere, and that has to go on sulfur. So you may see here, oh, sulfur does not have an octet no more. It has more than an octet. So we can say elements in the third row of the periodic table okay, so they can have something, they can have expanded octets. So you see this for structures like sulfur, phosphorus, argon. So argon does actually form some compounds. Well, not argon, sorry, xenon. So xenon's kind of a odd one of the noble gases. And that's because they have expanded octets. They can have access to d orbitals, and that can accompany lots more bonds. And you do kind of see this in coordination chemistry, or chemistry with metal atoms in solution that have bonds to solvent molecules or other ions and other what we call ligands. So you may learn about that. You'll probably learn about that in Chem 401. But they do have important roles in chemical industry. So there's always exception to the octet rule. So you have some that don't have an octet, like boron, and then you have some that have expanded octets, like sulfur, phosphorus, and metal atoms. Okay? So in this case, sulfur has 10 electrons around it. So that's an example of an expanded octet here. All right, now let's draw the Lewis structure for xenon tetrafluoride. So xenon tetrafluoride, just like we drew, sulfur tetrafluoride, we're just exchanging xenon for sulfur. Okay, so xenon is actually a noble gas. So xenon has 8 valence electrons. And fluorine has the same 4 times 7 equals 28 electrons. Okay. So in this case, now we have 36 electrons total. Okay. So xenon in this case, is going to look pretty much the same like we drew sulfur here. Xenon is the center. Then we're going to draw fluorine around xenon in like a square. Okay, so that's 8 electrons. Now we need 28 more. So if we distribute here, 2, 4, 6, 10, 12, 14, 16, 18, 20, 22, 24, 20. Let me count that again. Sorry. So we have 8. So we have 8 for the first fluorine and the bond. 8, 16, 24, 30. No. 32. Sorry, I can't count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons now. So now we need 4 more electrons, and those will go on the lone pair as lone pairs or non-bonding electrons on xenon. So we put both of the lone pairs here. So now it has a total of 6 electron groups around it. Okay. So elements in the first and second rows of the periodic table do not have valence shell d orbitals. Okay. They do not have these d orbitals in the valence shell. All right. So let's use the fact that nitrogen and oxygen do not contain 2d orbitals to explain why these elements cannot expand their valence shell. So they don't have access to the d orbitals, right? So they can't form an expanded octet, right? And that's because there is no d subshell in the second principal energy level. And that was mainly confirmed using the ionization energies. We didn't see a possibility for a electron in the second energy level past the p orbitals. So there's no verification for a 2d orbital. So there's no d subshell in the second principal energy level. Okay. So row 2 elements, right, cannot expand past an octet. So it's not possible for these electrons to form more than 4 bonds or 8 electrons around an atom in a compound. Okay, so it's not possible. All right, so let's move on to the last slide here. So let's talk about bond lengths. So in bond lengths, we define it as the distance between 2 atoms involved in a chemical bond, and it's usually the center of an atom. So usually we express bonds in units of picometers. So 1 meter is 10 to the 12 picometers, or 1 trillion picometers. So we didn't go over this before, but the longer the bond, the weaker it is. So So just think about it this way: the longer the bond is, the further the electrons, um, the further the nuclei are from each other. So it's going to be a weaker interaction. So it takes less energy to break it. So it's weaker. The shorter the bond, however, the stronger it is because the bond lengths shorten and the interaction between the both nuclei and the electrons in the bond, it's going to be a shorter distance, so it's going to be a stronger force of attraction. So, just think about it this way. If you took a twig, right, it's harder to break a shorter twig than it is to break a long branch. And that's because, it's just harder to it's hard to separate the sever the branch that way. So that's how I like to think about it. Okay. So the shorter the bond, the more energy it requires to break the bond, and the stronger it is. And that's because usually when we have shorter bonds, there's more electrons between the two atoms. So for example, here's a single bond here, double bond in the center for ethene, and a triple bond for ethylene. And you see here the bond lengths, they do seem to follow a pattern. The CH bonds get shorter as we move from left to right, 109, 110, 109, 106. But it's not as dramatic as the change in bond length for carbon, which is 154, 133, and then 120. So all these compounds are gases. They're used for a variety of things in our society. But don't worry too much about that. So that's why we kind of say, okay, if we have a double bond, it's going to take more energy to break than a single bond, and that's why they're considerably more sturdy, and they will require more energy to break in order to do a chemical reaction. Okay, all right. So let's wrap things up here with the last checkpoint of the day. All right. So which compound would you expect the oxygen-oxygen bond to be the longest? The O2 molecule that has its OO double bond, or hydrogen peroxide that contains a OO single bond? So let's just draw these two structures out here. So the structure of hydrogen peroxide is this zigzag character. So the thing about hydrogen peroxide, it has this very weak. Well, I guess I just gave it away, but hydrogen peroxide has this OO single bond here, and whereas here oxygen, we're just going to draw it in its not very stable state. We'll talk more about that later in the chapter, but this is what we call singlet oxygen. This is the excited state of molecular oxygen. Okay, so singlet oxygen is very reactive, and if it were the main source of oxygen on the planet, it would oxidize and cause things to combust very rapidly because it's not stable and it's an excited state of regular oxygen. Okay, so if we think about it on the terms of double and single bonds, we expect a OO double bond to be more stable than an OO single bond, just because the bond lengths are shorter. Okay, so what we can say is that the oxygen, single bond. So remember, when a bond's weaker, the bond length between two atoms is longer, so it's a weaker force of attraction. So the OO single oxygen single bond will be longer. Okay, and that's because well, we kind of went over that, right? The length of a single bond is greater than the length of a double bond. Okay, so that will be it for this lecture. I hope everyone was able to keep up with me. Upload the material as well. But if not, please just go back through the problems. Do it again more slowly because things are going to pick up from here. But I'll see everyone in the next video. All right, so take care.